Hello, we're RuleScape, and we are a rule-based optimization for genetic circuit design. Let's start out with a scenario. So let's say your PI asks you to make a NOT gate, and you know some of the rules from your personal work, and you ask some people in your lab, and they give you some tips, and you also dug some stuff out from lit reviews. This is the typical workflow that we're all acquainted with, where you're specifying and you're designing and you're learning along the way, and you're re-implementing what you learned into how you design and how you specify. Going more specific, the tools that you end up using to specify and design are generally Cello and Knox, where you're designing, simulating, and evaluating with Cello, and then you are specifying, storing, and visualizing with Knox. And you're going in between these two tools. And what we want to do is look into how to connect these seamlessly, and how to learn throughout that process as we connect the two tools together, and how to navigate a complex rule space while limiting combinatorial explosion. And that's what RuleScape is. RuleScape lets you evaluate which rules are the most important for optimizing the expression of the circuit.
Here's how the pipeline works at a high level for RuleScape. We start with a real experimental dataset, the classic single input library, which contains thousands of genetic designs, each with measured expression values, induced expression, fold changes, and a switch score. From that data, we automatically generate the UCF and CSV files that Cello and Knox need as inputs. Cello runs on those inputs and outputs expression scores for each design. Knox then evaluates user-defined rules against those designs. Finally, our machine learning algorithm, XGBoost or Random Forest, takes those rule evaluations and ranks them based on their predictive power for expression levels. The results? A ranked list of rules that tells you what design choices actually matter.
We use the classic single input dataset, which contains experimental measurements for large genetic design space, where each row represents one design with both structure and expression outputs. Our goal is to convert this dataset into inputs that Cello can use. In the classic loader script, we load the raw MATLAB data and combine the design and expression matrices into a single data frame. We rename the expression columns and compute a switch score, which ranks designs based on how strongly they separate low and high expression states, as shown here. The single input UCF writer shows that each selected dataset row is converted into a Cello gate, basal expression becomes Y min, induced expression becomes Y max, and then fold change is used to estimate hill parameters like K and N. The response function models a NOT gate where output decreases as input increases. In make Cello files, we generate the shared Cello files, including the input JSON for the sensor and output JSON for the reporter, and a Verilog file that defines the target logic, which here is a NOT gate. So finally, we call the make single input UCF, which sorts the switch scores and selects the top n designs, looping through each row to generate the structure, model, and gate entries. Here we chose 10,000 designs, so it should generate 10,000 gate entries. So overall, each dataset row becomes one candidate gate in the final UCF, giving Cello a data-driven library of designs.
We start by loading the classic dataset and parsing it into two data frames, one tracking part assignments per design and one holding the expression values. From there, we build a part library by mapping column prefixes to part types like CDS and promoter, giving each part a unique ID. We then convert each row of the assignment data frame into a comma-separated list of part IDs, where each row represents one complete circuit design. Both the part library and designs library are exported as CSVs, which feed into the next stage. We generate rules using Goldbar, then import everything into Knox. The part library, designs, and rules, alongside the expression outputs from Cello, converted into their own CSV, setting up the final scoring and ranking stage.
The machine learning pipeline starts with the GUI, where the user specifies which machine learning models to run, how to split the data, and how many top rules to return. This request then hits a fast API on the backend, which validates this input for the Python scripts and connects to the Knox API. From Knox, the design to rule data frame is then extracted. And in the ML pipeline, this data frame is formatted for the machine learning and passed to the Python scripts to run the selected models. Each model then outputs a summary that is passed along to the GUI. And in the summary, this includes the model name, its accuracy, and the top contributing features and their scores. A key limitation of this pipeline is the fine-tuning of the machine learning models, because users cannot specify every parameter for the machine learning model through the GUI, such as max depth of decision trees, which may affect the performance. All models are also decision tree based, and a future direction would be incorporating a larger number of diverse models. However, this would also increase the number of dependencies necessary for the software and the overall complexity.
So this is our landing page for RuleScape. As you can see here, we have our 4 stages. And yeah, so in order to host all of these, you can see we have a Cello service online. So we have a service that kind of continuously pings to see if the service is online. And we do this for Cello, we do this for Knox, as you can see down here. We also do this for the ML layer. And if I close one of these, so if we can do the cello one first. If I close the cello service, which is this tab, you can see it went offline. So let's start it back up. And so we basically have a terminal for each one of the services that we're hosting. So we have one for the front end, which is this terminal. It's our React front end. And then this hosts our cello service. This one hosts our ML service. And then this last one holds the Docker stuff for Knox. So going back to our landing page, we can then upload our files. So let's do that here. We'll do, it'll be cello input. We have some sample files that we've been testing with. So you can see here that the text is colored. It's the same editor that VS Code uses, but kind of the lightweight version of it. So you can see that all the things are colored appropriately. Let's upload our UCF, our input, and then our output. Okay, so after we do that, we can then choose the amount of candidates that we want to score. So the UCF file allows us to go up to 10,000. So let's try just 100 just to make this quick. Let's do the top 50 out of the 100 candidates. That's all fine. And then you can see here that it's running. And then if we check the backend here, we can see that it ran 100 designs. So it ran that. Now that we have our scores, we can then go to the next stage, which is our Knox stage. And once you run the cello portion of it, these 4 fields will auto-populate. If you just want to skip cello, you can also upload your own files here. This gives you the option to download the files that were generated. And then now we put in our gold bar expression. Let's go to Knox input. For our gold bar inputs, we basically just had a AI generate a bunch of rules for us, as you can see here. And you can see later that it won't necessarily do well for our scores, but it's just for testing purposes. So let's go ahead and import this bundle. And the bundle will be these 4 files, or I guess these 3 with these 2 files. This is just a summary. And then let's evaluate the rules. And this is just a little snapshot of what we get. So there we go, Knox completed. You can see here that it was completed. So let's go to the next stage. Let's just choose all of the ML models. And they ran, so you can see we got 50% here, 43% with random forest, decision tree 50%, and an R score. Now in the last tab, it's a summary of everything that we've done. So it kind of tells us what all the files that we did, the parameters that we use for everything. So you can see here the pipeline, configure cello, review Knox, and then basically just all the inputs. And yeah, this is just basically a front end.